All right, so now we move into lesson 10, which is projectile motion. It's the last lesson of Unit A, which is kinematics, and it puts together all of the skills we've been talking to at this point. So on our next slide here, let's just do a recap. In lesson 1 to 2, we talked about uniform motion and how our top left equation is always the one we resort to. We then went to lessons 5 to 6, and we said, hey, let's now add more kinematic formulae, aka the formula that responds to acceleration and all the different options we had there. In lesson 7 to 9, what we did is basic vector addition and looked at a ton of relative motion and said, well, how can we put together vectors and represent motion in terms of different degree angles and overall resultants, and talking about a resultant maybe in terms of a displacement, velocity, or acceleration and how that could be looked at. Now what we're going to talk about is projectile motion, where projectile motion is simply just saying, if I have any object that travels in this parabolic trajectory, I might have this accelerated motion, which represents projectile motion and coming together with all these equations. So we're essentially putting together all the knowledge we've learned to this point into one type of problem, which is projectile motion. Okay, now examples of projectile motion. Here's what we have. We have a bunch of different scenarios in which it could occur, and here's what they all break down to. In the first example, we would consider this to be an object that is thrown horizontally off a cliff. And so if you want to throw in that tagline here, I'm just going to zoom in and say, this is when the object is thrown horizontally, and this would be thrown horizontally off the cliff. There we go. Now, in the next example, we would consider this one to the right, some object that is being launched at an angle and returning to the same height. So it is launched from a height and returning to that same height. There we go. Now, what I want to put on here is a couple very, very key specific details here. In these first two, before I classify anything more here, what I'm going to do is say that if I look at that first one, I'm going to have some sort of Vx or some sort of speed in the x direction. I'm also going to have some sort of vertical direction speed, but in this case, because it is being launched horizontally, I'm going to classify my VIY to be 0 meters per second at that given point. And we'll talk about that more in the upcoming examples here, but that's something we really want to say. The other piece I want to make a note about is that the final velocity, we're gonna find out that the Vx is actually the same thing, but we cannot say that our overall final velocity is 0. If you say that the final overall velocity is 0, it's going to make a ton of mistakes on these problems. Now, in the other one, where we launched from the same height and then returned to the same height, it is going to be launched at some sort of positive initial velocity, and so I'm going to call this Vi. It's going to end with the same velocity, but in the opposite direction. And in class, I often called this the equal and opposite magnitude. And so I'm just going to make sure I fill in this arrow using a more straight tool here. So there we go. And this is going to be a negative VF because it's going in the other direction. Even though it's the same magnitude, it's in the opposite direction. And then right at the very top, we found out from even our labs from before, we said that right at the top where it transitions from positive to negative velocities, this is 0 meters per second, right at the very peak. Now, in classifying the last two here, we look at these and we say, well, it's launched at an angle of some sort and then off the cliff. So I'm going to say at an angle off the cliff. Off the cliff. And these don't have to be cliffs, but it's just easy to think about them like that. And then this one is at an angle and getting launched onto the cliff. Perfect. So any of these projectile motion problems could appear. Namely, we're going to see a lot of the first three, aka this one here, and this one here. And then the nice thing is these two are directly connected to one another. Once you know how to do these ones, you can actually do these ones because they follow the same principles here. Okay, now looking at projectile motion, this may be a slide you want to revisit before any major sort of assessment. I would definitely revisit this because it talks about how we view the vertical and horizontal components and what principle gives us this idea behind projectile motion. So projectile motion is this idea that we put in the principle of combined independent motions. And what that means is that we're going to have some sort of vertical component and some sort of horizontal component. And these things happen at the same time, but the most important thing is they act independently of each other. So combined independence meaning both of them are happening. They're happening together, but they're independent of one each other. And here's how they're independent. The vertical direction or the vertical component is affected by gravity, and thus it's accelerated. And so I'm even going to fill that in here. It faces acceleration. Namely, the acceleration it faces in these problems is g, or gravity. Now, in terms of the horizontal problems, we would say that the horizontal situation is uniform throughout, and it's uniform because it does not change. And I want you to write in that note for yourself, the Vx does not change. So I'll be specific and say just first of all that it doesn't change. What doesn't change? The speed in the x direction, because our x direction is not being accelerated. Now, the most important thing on this slide, besides that independence principle, is to star this here and say that the variable that is consistent between both sides, the vertical to the horizontal, as these things act independently but in combination, is the time. And if I can solve for the time, I can actually pass information backwards and forwards as much as I want, and it's really important for us. And again, we're going to ignore air resistance just like we have throughout the rest of Physics 20, and even including into the units B, C, and D. We're going to continue to do that, ignoring air resistance and friction in some cases, so this is nothing new to us. Okay, now let's break apart some diagrams here before we get into some problems. And there's a really important piece I want to pull out of here, or a couple really key critical things. And the first one is the following. Suppose I was taking an object and I launched it horizontally off a cliff. Well, the one thing I want us to be very aware of right away is if you look at the magnitude of the Vx along the entire way down, the Vx is not changing no matter what because it's uniform motion. And so I really want you to draw that in for yourself. Say that Vx does not change. And to short form it, what I'm going to say is that this is uniform motion, or UM, as I often write it in class. Now, if we throw something horizontally off a cliff, the initial vertical component is 0. That may be the other thing you really want to highlight here. And I know there's the red arrow going to it or the arrow pointing to it, but what you could write in here is say that VIY is equal to 0 meters per second. The reason that your VIY, or your initial velocity in the vertical direction, is 0 is because when it's launched horizontally, it's not moving up or down at that very instance, it's just purely moving horizontal. And so that's a really key thing there. The other key piece that before we move into our second example, or second, I should say, second visual that we're going to break apart is the following. If it started at 0 in the VIs, then as VI goes down, we're going to see that because acceleration is affecting the variable or affecting the object in the y direction, acceleration is pushing this object down in the vertical direction, we're going to see that the overall magnitude of the Vy increases as it goes towards the ground, meaning that the velocity has more magnitude towards the bottom of the cliff than it would at the top in the vertical direction. And hopefully that makes sense, because as an object has accelerated, its magnitude should increase. Now, the part that they're pointing to in blue here is just referring to the Vx not changing in both of these. And again, because the Vx remains the same no matter what type of parabola we're looking at, or no matter what type of projectile motion we're looking at, the Vx that's symbolized by this blue, it does not change because we know that it's uniform motion. Nothing is accelerating this object in the x direction. Now, something to point out from this second diagram here would be the following. I know when I get to the very peak right here as the thicker black dot, I realize that my Vy at that point is equal to 0 meters per second. It is not traveling in the vertical direction at any point here. So what I want to say is that right at the very peak, it's not that the overall velocity is 0, it's that the Vy is 0. It's not moving up or down. It's still going in the x direction at that point, just not changing at all vertically in that case. Now, the other thing you want to recognize from here that I'm going to highlight in green to keep it uniform from the last diagram, if you see your Vy's are originally very long in the beginning because the initial velocity is really strong in the cases of it going up and returning back down to the same spot, as it goes towards the peak, it's going to lose a lot of that magnitude and to the point that it becomes 0. And then on the opposite way down, the only thing that changes is that the Vy is now in the opposite direction. But as you can see, and I could even draw a connecting line between these two things, if you see the original green line and then the green line over here, they're actually the same magnitude. They're equal and opposite though. And so we just want to be very careful with that and say, hey, as we look at these parabolas, and because they follow this perfect symmetry, we're going to see that they're equal and opposite across the parabola. It just means that the magnitude's the same, the sign or the direction in which the object is traveling is opposite. Okay, now let's propose a situation here. In this situation, this person is going to fire a bullet from a gun horizontally. And then at the same time, what they're going to do is drop a bullet just right next to them. And they say, which hits first? The one where they just drop it or the one where they shoot it horizontally? And this is the big thing we need to be very aware of here. When we're either shooting the gun horizontally or dropping the bullet, both of them follow the same acceleration. And what I mean by that is both of them accelerate in the vertical direction by gravity. So in fact, when they say which one hits first, let's consult our diagram over here. Suppose the yellow is the one that was shot out of the barrel. And then suppose the red one is the bullet just being dropped side by side here. Well, what we want to think about is at each key interval, you can clearly see that the ball is at the same position. Even if it's a little bit further out in the x direction, the ball maintains the same vertical height at any given unit of time. And so when they ask us which one hits first, they actually hit at the very same time. So at the same time. And we could go further into this and say the following. If we look at these ones, the reason they hit at the same time is that just because the object, whoops, and that skipped over. There we go, I'm gonna go here. Just because the object is traveling horizontally or moving in the horizontal direction, it does not mean that the gravity does not act on the objects in the same way when falling vertically. And what that means is whether I shoot it or whether I drop it, I know that the object is going to fall at the same rate because they both experience gravity. And even with that extra x velocity or that x speed, the speed is just a determinant of how far the object goes out. Meaning, if I was to look at this visually, the x, all it does is contribute to how far it lands away from the original starting position, but it doesn't actually contribute to anything in the air time, because rather than thinking about this in terms of x having any sort of impact of air time, unless there was like strong air resistance or something that was lifting this object in the air, yeah, we can make a case for it. But overall, at the physics 20 level, we want to look at this and be like, the only thing that affects both of these objects once they're released is gravity. And if gravity is the only thing that affects both these objects once they are out of the hand of the person or out of the gun, it means that they'll fall at the exact same rate, regardless of the mass of the two objects or regardless of the situation, because they both fall at the same rate. But this only applies if they start at the same height and they end at the same height. If I fired a gun vertically into the air, this would be totally different, because if I dropped a bullet and then fired one vertically into the air, they're going to land at totally different times. It's only if they exactly start at the same position and end at the same position. If I have something that goes along the horizontal, it won't affect its overall time in the air. Okay, now projectile motion calculations. This one is another one of those slides you're going to definitely want to revisit before any sort of major assessment. This is one of those study slides that you're going to really need to pay attention to. So when we're dealing with projectile motion, we need to break it into its horizontal and vertical components. The vertical components are the following. The vertical components are accelerated. They're facing the gravity behind this problem. So they're going to involve the following variables: dy, viy, vfy, acceleration, and time. And so I like to just make sure that they always have their scripts on them, just to make sure that we're representing them in terms of, are they going horizontally or vertically? When we talk about horizontal calculations or the x component, it's always uniform motion, and we only have three variables, and we can only use the one equation, which is right at the very top, and that is that speed is equal to distance in the x divided by time. So we must use that first formula on there. And then the last thing I want you to be making sure that you're aware of here is that point that's right at the bottom here. Remember that the only thing that connects these two is time. And if you need to, what I would highly do is circle the time here, connect a line between them. Because essentially what we want to do is we want to indicate that these are the only variable that can communicate. I call this the communicator between these, or the universal communicator. So if you can get time, you can go backwards and forwards between vertical and horizontal, and vice versa. Because otherwise, we have no tool that directly connects these things. They're independent, or they're combinedly independent, meaning if I have two of these things, the vertical and horizontal components, yes, they're happening at the same time, but they're independent of one another towards the problem. So time will be that nice connection that we always need to figure out. All right, let's try an example here. An object is thrown vertically off the cliff, and it's thrown vertically off a cliff that is 100 meters high. It strikes the ground 90 meters from the base of the cliff. At what horizontal speed was the rock thrown? Okay, let's put it all together in a visual. So what I'm going to do first and foremost is I'm going to draw a visual of the cliff. Here it is. I'm going to draw some sort of parabola representing the overall motion of this object. And so it's going to look like the following. I'm going to draw, maybe in blue here, I'm going to draw it directly horizontal, and then it crashes down over here. Pretty good. There we go. Okay, now we want to label it with all the correct visual stuff here. So first and foremost, I'm going to put in some sort of Vx, because if it's launched horizontally, it has some sort of overall speed in the X direction. And one thing you could do here is you could say, because that I know that the speed in the X direction is not changing, why don't you just put a couple vectors that represent that this magnitude is not changing, it is a uniform quantity. The other thing we're going to put here is that the VIY, or the initial velocity in the Y direction, is 0 meters per second. The reason we can say that is because when it's horizontal, it's not moving up or down. This is a 100-meter high cliff, so I'm going to make the change in Y, and I'm going to change this to a black marker here. The change in dy, or the displacement in the Y direction, is negative 100 meters. And you're probably thinking like, why am I putting negative 100 meters? Isn't this an up direction? Isn't it like 100 meters off the ground? You always got to be thinking about what direction does the object fall, not overall what am I observing in real life. It's how is the object in relation to what is the surroundings. It's falling 100 meters. Then the other part is we're going to draw in right at the very bottom here. They said that it is 90 meters from the base of the cliff where it strikes the ground. So to be more specific, I'm going to say that this is the distance in the X direction, which is equal to 90.0 meters. Okay, now we're going to try and solve this all right here. So here's what we can do. First and foremost, I'm going to label my variables. So I'm going to label this and say, well, because I'm trying to solve for, and I'm going to give you a hint about how to solve these things right away here. If I know that I'm solving for something in the X, namely, they say what horizontal speed was this thrown, aka they want us to solve for the Vx, we're going to have to use acceleration to get time, and then transfer that time value over to the uniform motion. Because we're trying to solve for something in X, you know it's going to be your last step. And so here's what we're going to do. I'm going to label all my variables. dy, which is the first one. We have VIY. We have VFY, acceleration, and change in time. And remember, we want to write out all the variables because we need to identify an equation that would match us up for this. So I'm going to put negative 100 meters, which is that first variable we knew. We knew VIY was 0 meters per second. They didn't give us anything about VFY, so I'm going to say that that doesn't matter. Not that it's 0. That line with throughout the 0 there, that's just saying that we're going to ignore it for now. The acceleration, these are free fall problems, so I'm going to write negative 9.81 meters per second squared. And then the change in time, this is that really critical one. If you even want to on assessments, you could highlight it. Once you say that this is the question mark, you can be like, I need this variable or else I can't transfer information from one to the next. Now, the equation that would line up to this is the following. We would get that the displacement in the Y direction is equal to VIY times time plus 1/2 AT squared. Because of that key information, that's what I'm going to place. We know that our VIY is 0, so this is a really nice formula to select because I can actually cancel out that first term. This is going to give me displacement in the Y direction is equal to 1/2 AT squared. And now, because I'm trying to solve for the time here, whoops, I'm going to make sure I have my variables in there, AT squared. There we go. Because I'm trying to solve for my time, here's what the time looks like once I've isolated it. It is going to be the following. T is equal to the square root of 2 times dy divided by the acceleration. Now, when I solve for time and I put in all the magnitudes, it's going to be time is equal to the square root of 2 times the displacement, which is negative 100 meters, divided by negative 9.81 meters per second squared. And this is going to give us a value of 4.515 seconds. There we go. So now what you'll want to do is, this isn't the final solution, but we're going to highlight it and say our time is equal to 4.515 seconds in the air. Now it comes for step number 2. Step number 2 is to say, if I've used the accelerated motion to now solve for time to get the speed in the X direction, I'm going to use the uniform motion equation. So step number 2, I list my variables. dx was equal to 90.0, or that's the distance it travels in the X. I'm going to say that my speed in the X is unknown. I know that the time spent is the same as the previous part, so 515 seconds like this. Now, in order to get our speed, we say Vx is equal to dx divided by time I'm going to plug in my values for D, which is 90.0 meters, divided by the time, which is 4.515 seconds, and therefore my speed in the x direction, because this is a scalar quantity, is equal to 19.9 meters per second. There's my answer. There we go. And so if you're wondering again, why did we use accelerated motion first and then we used our uniform motion second? It was because we looked at this and said, okay, I need to use the accelerated equation because I don't know enough information about the x's. And furthermore, in all these problems, it's going to be this pass of the baton of solve for time in either accelerated motion or uniform motion, and then pass that time to accelerated motion or uniform motion. So it's always this backwards and forwards between the vertical and horizontal. And if you really wanted to classify it, you could say everything in the accelerated direction, this is your vertical. Everything in the x direction, this is your horizontal motion or your uniform motion. All right, we're going to do another problem that's very similar to this one here. So here's the problem here. Example number 2, another object is thrown off a cliff horizontally. So here's what we're going to do. We're going to build out our cliff diagram again. So there's my cliff. I'm going to do, again, some object being thrown off horizontally like so. I'm going to put some sort of vector which represents my Vx like this. And if we wanted to, we could draw some more Vx's on here to indicate that it doesn't change. So this is our Vx, this is our Vx, and this is our Vx that isn't changing. It's thrown off horizontally, so I'm going to call this VIY equal to 0 meters per second. The initial speed in the y direction is 0. And now here's the formal definitions of what's happening here. An object is thrown off a cliff that is 65 meters high. So what I'm going to do is go change in displacement in the y variable is equal to negative 65.0 meters. Now again, you're like, why are we putting a negative? It's because it's going down the cliff, not up the cliff, but down the cliff. We're not thinking about the physical object in reality. We're thinking about if it's 65 meters up the cliff, how does the object move in relation to this? Now, it moves at a horizontal speed of 35 meters per second. So what I'm going to do is instead of just putting Vx there alone, I'm going to say Vx, or the speed in the x direction, is 35.0 meters per second. And again, we know this is a constant value because Vx is not accelerated, it's uniform motion. Now, the last part of this problem says, what is the distance from the base of the cliff to where the object lands? aka, if I put a dotted line here, we're looking for the distance in the x direction. Now, what you're going to notice is that this solves very, very similar to what the problem we just dealt with here. So let's start off with, because we don't know enough information in our x direction, or that's what we're trying to end with, let's deal with the accelerated components, aka the vertical direction. Once we get our time, we can pass it forward and figure out what is this distance. So here's how that's going to solve. Part number 1, we're dealing with accelerated motion. We have displacement in the y, we have our VIY, we have our VFY, acceleration, change in time. Okay, change in time. Again, I'm going to always highlight this one because I know it's so critical, so important for us. And then with all these other ones, I'm going to say this is negative 65.0, and this was meters. We have a VIY of 0 meters per second because it was launched horizontally. VFY doesn't seem to really matter to us. They don't really indicate anything about that one. And then our acceleration is always negative 9.81 meters per second as long as it's close to the Earth's surface. And we're going to see in the later units that this acceleration might change, but for kinematics, it will always be in free fall at negative 9.81 meters per second. Now we're going to apply a formula. Again, the nice thing is because the setup is very similar, I'm just going to go right back to that original equation. VIY times t plus 1/2 at squared. There we go. We're going to cancel out our VIY times t because that would multiply to make 0 if VIY is 0. This means that we're going to have the following. If I solve this for time, just like we did in the last one, I'm going to get time is equal to the square root of 2 times the vertical displacement, or dy, divided by the acceleration of free fall. And this is going to give me t is equal to the square root of, we're going to multiply 2 times negative 65.0, and this is meters, close the bracket, divided by negative 9.81 meters per second squared. All right, therefore, our time value that it takes from the top of the cliff to the bottom of the cliff, if this is thrown off, is 3.64 seconds. Now, once you get this time, I want you to highlight it, box it, make sure you highlight this or make sure you make it important. You could circle it, you could star it, whatever you want, just to make sure that you're not losing track of this value, because it's our universal communicator of how we go from accelerated motion to uniform motion. So now to end this problem and get the dx, here's what we're going to do. We're going to go part number 2. Let's deal with our uniform motion section. So we have distance in the x, speed in the x, time. We know that the time is going to be the same, so 3.64 seconds. That remains uniform. The Vx was equal to 35.0 meters per second. The last thing we're trying to solve for here is the distance it goes in the x direction. We're going to start off with our original equation, v equals dx over t. I'm going to multiply up the t to both sides. So let's put this in brackets. Brackets around this one too. Multiply them by t. I'm going to get dx is equal to vx multiplied by the t, which means this is going to be equal to 35.0 meters per second multiplied by the time it spends in the air, which is 3.64 seconds. Therefore, the horizontal distance this thing travels while it's in the air is equal to 127 meters to the nearest third sig dig. So there we go. That's why, if you're thinking, why did I just round this to the nearest whole number, no decimals? Well, we go back up to the problem, and there was 3 significant digits on both of the pieces of information from the problem. So I'm just going to make sure I have that again. There's my answer. And again, you see that very similar format where we have some sort of Vx value. It could be known or unknown. We have a VIY of some kind. We have a vertical displacement. We have some sort of horizontal range or distance. And then in these problems, based on the setup, we were trying to solve for something in x, so we had to solve using acceleration first, and then pass the time information, or pass that baton of time over to the uniform motion, so that we could figure out, based on that problem, how far it traveled horizontally. All right, now looking at example 3. Example 3 says that what if we have an object thrown horizontally off a cliff again? So we actually get another example of it, and just this is going to really solidify all the skills behind this. But what we're going to notice is that maybe the order in which the problem is solved is slightly different. So here's the situation. If we know that this is thrown off a cliff, I highly recommend just drawing out the diagram yet again. And so I'm going to fill this in, and I'm going to draw the horizontal projectile. I'm going to fill in that there is some sort of Vx here. And so I'm going to put the magnitude arrow, and then maybe I'll do like 1 or 2 more here just to show it's uniform. I'm going to fill in the information about this, saying a ball is thrown horizontally at 12 meters per second. So I'm going to write at the very top, just fill in that our Vx is equal to 12.0 meters per second. I'm going to put in my VIY is 0 because it is horizontally originally. So if it's horizontal original, then we know that it's not moving vertically in the sense of any sort of speed. So we got to make sure that I put that as 0. I'm going to put the distance of the cliff, or how far it has to go down. So a ball is thrown horizontally from this building and lands 25 meters from the base. How tall is the building? Well, that means that our vertical displacement, or our change in the dy, is unknown. So I'm going to put this as equal to question mark. They tell us that the ball lands 25 meters from the base. And so I'm going to be specific and say that this represents our distance in the x direction, which is 25.0 meters. Now they want the dy. Okay, here's what we're going to do to solve this problem here. We're going to put this first and foremost. I want you to look overall at what's happening in the problem. We're trying to figure out something in the accelerated components, or we're trying to figure out something in the vertical direction. And so if we're trying to find something out in the vertical direction, that means most likely we're starting in the horizontal direction. And so what I'm going to do is, instead of dealing with acceleration, we're going to start off dealing with the uniform motion. Here's what our values are. We have a Vx, we have a dx, and we have time. Okay. The major variable we're looking for is this one here. We got to figure out what the magnitude of the time is. That's our question mark. So I'm going to put a question mark here. The dx, or the distance in the x, is 25.0. The speed in the x is 12.0 meters per second, and that doesn't change regardless. So now we're going to go to our uniform motion equation and say that Vx is equal to dx divided by time. When we do this, we're going to figure out time, I'm going to swap these two variables because I can multiply and divide them up. This is going to give me time is equal to distance in the x divided by the speed in the x. And when I plug in the magnitudes here, I will get that time is equal to 25.0 meters divided by the certain amount of speed, which is 12.0 meters per second. Now, it's always important you put in the full magnitudes and the full units just to make sure you understand what you're talking about. And then you would eventually see, because you have units, the meters cancel. I'm going to say that this is equal to time is equal to 2.083, and that 3 repeats, but that's okay. We're okay to just keep maybe 3 decimal places for this and then highlight it. And the reason I'm highlighting it again, it's not the final solution, but it's that key piece of information that allows us to communicate between the two parts of this problem. Now I'm going to go to number 2, which is below. Number 2 is our acceleration motion component. And so I'm going to go number 2 and fill in all the variables here. We have our distance in the y, VIY, we have VFY, we have acceleration, and then we have change in time. Now I'm going to put equals behind all these. I'm going to make sure they all have their vector tails on them or their vector symbols above. The dy, or the displacement in the y, that's what we're looking for. That's our question mark. So I'm just going to make that a little bit neater. There we go. Our VIY was 0 meters per second because it's thrown off horizontally. Our VFY, we actually don't know, and maybe we don't care about. So I'm just going to put in that we have we're just going to ignore it. That's the variable we don't need. Acceleration is always going to be negative 9.81 meters per second squared because it's an object in free fall close to the Earth's surface. And then the time is 2.083 repeated, which we just truncated down to 2.083 seconds. Now, again, because this is the variables we're given, this makes it really, really easy for us because we just use the same formula we've been using. dy is equal to VIY multiplied by time plus 1/2 AT squared. Now, if this is the case, we know that VIY is 0. This cancels out because our initial velocity in the vertical direction was 0. Now, my dy, we don't even need to do any algebra here other than just say dy is equal to, and start plugging in our variables. dy is equal to 1/2 times the acceleration, which is negative 9.81 meters per second squared, multiplied by the time, which was 2.083 seconds. And I want to make sure I can get this as neat as possible here. So 2.083 seconds, bracket, and this is all squared just to make sure that I have that there. Therefore, my displacement in the y direction, or the height of this building, is equal to, well, according to the way this problem comes together, I should get negative 21.3 meters based on the algebra of this. But they asked me for the height of this, so what I would just say is right below, this is totally fine to highlight. I'm okay with you doing that, but what you want to do is use a sentence to say, yes, the algebra tells me that it's going down the cliff, so it's negative 21.3 down the cliff, but it means that the height of this building, the height is 21.3 meters. And if you just include that light sentence below there, you don't need an essay. You don't need to write me up some sort of like Shakespearean novel. I'm not looking for that. I'm just looking for you to say, if this is my answer, then according to the context, I want to say that the height is equal to the 21.3, which is the total magnitude. All right. Now we go on to example 4, where the object is thrown off horizontally, but it's not really an example, more of a summary towards our last problem. So if we look back to our last problem, from example 3, we wanted to reflect on the 2 physics principles that must be used to determine the height of the building. Then, once we know those 2, we're going to use the numbers on the data sheet that match in order to figure out which they are used and in what order. Meaning, if you flip over your data sheet, what you actually see is this section on the bottom left called the physics principles. And what we want to do is we want to put them in the order in which we use them for the last problem. So in the last problem, we did uniform motion first, and then accelerated motion for number 2. But on the physics principle sheet, here's what it looks like. To answer this, we would say step number 1, we used uniform motion, which is symbolic of 0. So 0 is the uniform motion. All right, for number 2, step number 2 of that problem, we used the accelerated motion, which is number 1 in the physics principles. There we go. And so your overall answer, if you were to answer this on like, let's say a numeric response, you'd be like, oh, this is 0 and 1, or I used uniform motion, then accelerated motion. And there's just like in example 1 and 2, we actually did the opposite. Rather than using uniform motion first, we used accelerated motion first. And so this answer would have been 1, 0 instead of doing it as 0, 1. But it depends on the order in which is required to solve. And order does matter because based on the information given, you have to go one direction or the other. And it's not an optional thing of, hey, let's just use uniform motion first always. That doesn't work. You have to figure out which order it was in order to actually solve for that time first and then pass that information forward. And you'll see what I mean. Not every problem can just be like, oh, I'm going to start with uniform motion, then use the accelerated, or start with acceleration, then go uniform. It just doesn't work that way. It's all dependent on the information given. All right, we got 2 more examples here. These are what I would deem maybe just a little bit more complicated. And so here's how we're going to solve this here. And this is going to require that lesson 8 and 9 material, and even including 7. So pretty much 7, 8, 9, where we have to break these things in terms of triangles into their components and then use the components to help us solve. So here is the overall problem. A ball is projected at an angle 37 degrees up from the horizontal with a speed of 20.0 meters per second. If it comes back down to the same vertical height, how far does it travel horizontally, or what is the horizontal range? Now, in Math 20-1, you would call the range the y value. But for our case, we say that this is actually symbolic of the x value, or the x overall distance that this travels. Now, a couple major things to highlight that are important to this problem. The vertical velocity is 0 at the max height. Really important. AKA, when I talk about Vy at the max height, it's 0. And then the other major thing we want to talk about is if the projectile is launched and ends at the same spot, we now need to, or launch and ends at the same vertical height, we want to say that the velocity initial is equal to the velocity final. They're equal in magnitude, opposite in direction. So now let's draw out the problem here. Here's what you're going to have to do. I want you to draw just like a simple parabola that looks like this. Now, we're going to put a ton of labels on this thing because we need to make sure that it is according to what our problem is. So first and foremost, you're going to draw up your arrow indicating the initial velocity. And then what we can do is at the end, we can actually draw that same arrow just in the reverse direction. Now, the other thing we can do about this is we can draw in our components. We have some sort in the x direction, some sort in the y direction. So what I'm going to classify this as is VIY, or the initial speed in the y direction, and then the initial speed, or the initial speed in the x direction. Now, they told us that this object travels at 20 meters per second. That's going to be the hypotenuse here, 20 meters per second, and it is positive because it's on the way up, and so we consider that hypotenuse to be 20. And it would be 20 on the reverse technically, but what we want to be always assuming about this is that the hypotenuse magnitude is a composition of those two others. Now, I'm going to make this 37 degrees on the interior, so make sure you do that as well, 37 degrees. I'm going to include a label what the speed is at the top, or what the velocity is at the top. Right at the very top, we would say that the Vy is equal to 0 meters per second. There we go. And some other critical information, I think we might have it all here, is that the last thing I may want to add here is that we also have the opposite direction where the velocity is in the negative direction, velocity is in the east direction, and so this would also be symbolic of Vx. This would be symbolic of your Vfy in the opposite direction. So if you really wanted to, you could show how it starts and ends with the same triangular tip-to-tail vector addition, and that might be the other thing. Now, very, very last thing is in this problem, they wanted the horizontal range. So what I want you to do is put a dotted line on the bottom and say dx, or the range, is equal to question mark. Great. Okay, we have everything set up. Here's what we're going to do first. We're going to break it into the components of VIY and Vx. So step number 1, in order to break this into the components, I'm going to say first and foremost that Vx is equal to, well, Vx is actually in the adjacent position, and we have the hypotenuse. This is the cos ratio, 20.0, and this is in meters per second, multiplied by cos of 37. Now, this is going to give you a value of a speed in the x direction of 15.97. And this is meters per second. Okay, now we want to get the y. VIY is equal to 20.0 meters per second. And because it's now the opposite over the hypotenuse, or opposite over hypotenuse, we're going to use the sine ratio, so sine 37. And that's kind of the nice thing about breaking into the components. When you break these things into their components, you're always using one ratio, and then whatever ratio you use first, the other one is just the opposite ratio. So if I use cos to get the Vx, then I know I'm going to use sine for Vy, or vice versa, depending on the problem. So this ends up being a magnitude when I go 20 times sine 37 of 12.04, and this is meters per second. Okay, now I think we're okay here for the most part. There we go. Okay, now what we're going to do is we're going to take these components, and if I know that these are the components, now I can start solving this in terms of a regular projectile problem, because that 20 meters per second they gave me really has no bearing. It's both the vertical and the horizontal combined together. Now that I have them separated, we can do a very similar procedure to what we have done before. Here's step number 2. Once we have it in the components, I'm going to now use the accelerated motion in order to figure out time, because my end goal is to solve for something in the x. And so I'm going to write displacement in the y is equal to, I'm going to write VIY, VFY, acceleration, and then change in time. Well, filling all these variables in based on what I have, if I look at this, I know that because this thing starts and ends in the same manner, my VIY and my VFY are reflections of one another. And so I'm actually going to directly connect this to this. All I need to do is make them the same magnitude, opposite. So dy, there wasn't any information given about vertical displacement, and if it starts and ends at the same position, you know that this just means it's 0. So realistically, if you wanted to put 0, you could, but I'm just going to write it doesn't matter for this case, because they didn't even give us information on it, so I'm just going to leave it at that. So we have the dy had no bearing on this problem, positive 12.04 in terms of the VIY. We're going to get negative 12.04 meters per second. For the VFY, acceleration was equal to negative 9.81 meters per second squared. And then the change in time, again, I always like to highlight this one because I'm like, hey, it has a huge implication on how we solve the rest of this problem here. Now, the equation we're going to use in order to solve for time based on these variables coming together is acceleration is equal to VFY minus VIY divided by the change in time. Now, change in time, I'm going to swap that with acceleration, VFY minus VIY, and then divided by the acceleration. When I plug in all the magnitudes, I get change in time is equal to, we're going to start off with VFY, 12.04 meters per second. This is going to be minus the positive 12.04 meters per second. There we go. And then divided by the acceleration of negative 9.81 meters per second squared. Okay, change in time, and I'm just going to write that just a touch lower. Change in time is equal to, and what we're going to find is that it is 2.455 seconds. There we go. And again, this isn't a final solution. I'm just highlighting it. All right, now once we get this piece, we're in the home run stretch. We've broken our components apart, so we now have a Vx, a Vy. We use that to figure out what is the change in time, or what is the time this object is in the air, using the acceleration equations or using our vertical components, our vertical direction. Now that we have our time, we know that the time spent in the vertical direction equals the time spent in the horizontal direction. We wrap this up using uniform motion. Therefore, step number 3, Vx. And we could actually put together our variables, so maybe I'll do that just depending on the space we have. Yeah, we have enough space for this. So I'm going to say step number 3, we have Vx, dx, and we have our change in time, where change in time is equal to the 2.455 seconds. We have a dx, which is the unknown. The distance in the x is what we're actually trying to solve for. And then our positive Vx, or our Vx in this problem, is equal to 15.97 meters per second. Okay, putting this all together in the formula, we say that Vx is equal to dx divided by time, which means that the equation becomes the following. Dx is equal to Vx multiplied by time. And now putting it all together, I get a distance in the x, which is equal to, I'm going to put it as 15.97 meters per second, multiplied by the time, which is 2.455 seconds. This therefore gives me, and yeah, I can shift this up just a little bit and keep it all on the one page. I was like, maybe I shift it to another page, but I think I'm good here. There we go. I'm going to say, therefore, the distance this object travels in the x direction, given that time and given that overall, the way the projectile went, is 39.2 meters. And that is to the 3 significant digits that we're looking for. So there's our final answer. All right, now using some red arrows, I'm just going to indicate our path to getting this answer. We drew a diagram. We then broke our answer into the components of, we had a certain speed in the x, we had a certain velocity in the y. We then passed that information forward and said, okay, now I have enough information to figure out whatever the change in time is given the acceleration equations. Once I figured out time, I could then jump over to my uniform motion equation and summarize my final answer using the uniform motion equation to get the overall distance traveled in x. All right, we got one more example here. Let's take a look at this one here. Again, this one is, rather than being a perfect parabola where it starts and ends at the same vertical displacement or starts and ends at the same vertical distance, now what we're going to have is something that is at a different vertical height when it changes. Or more importantly, one thing you may want to highlight before we start the problem is that if it travels and it ends at a different height vertically, we cannot say that these things are equal and opposite anymore. So the final velocity is not just equal to the negative initial velocity and vice versa. All right, here's the overall situation. A cannon is fired 36 degrees above the horizontal with a velocity of 180 from the edge of a 125-meter cliff. Calculate where the cannonball lands on the level plane below. So let's draw out a visual to help us out with this. So here's the visual. We're going to draw the cliff to start. I'm going to draw that the object is projected at some degree. So it's maybe going to go up and then come back down like this. And hopefully that gives us a little bit. Maybe I'll freehand it just so I can make sure that this thing kind of has a nice 36-degree angle. There we go. And then it crashes back down into the point that it hits the ground. Now, something that I really want to put in here right away is that our VFY, or more importantly, our velocity final, I'm just going to write it as VF, is not equal to 0 meters per second. That is definitely not true. If we make that assumption that it comes to rest like this, we're going to be doing the wrong thing. So let's not do that. The other thing I'm going to add here is the following. I'm going to draw in the vector arrow like this. So this represents our initial velocity, where the velocity, and I'm just going to draw it as, because I don't want to confuse it with VIY or VX, I'm going to say that the velocity here originally is equal to 180 meters per second. There we go. Now, this can be broken apart into the following triangle. We have some sort of Vx. We have some sort of Vy that by tip to tail vector addition combines these two together. So VIY is this one. All right, I'm going to throw in the degree angle here. So this is 36 degrees on the interior. And then based on this other information they gave us, they said this object gets launched up, but then falls down the cliff that is 125 meters tall. So I'm going to say that the change in vertical displacement, or the dy, is equal to negative 125. And again, I hate to sound like a broken record, but it's like, why do we say it's negative 125? Because the object is falling by that amount of overall displacement. Okay, now what we're going to do is we're going to solve out for our first piece here. The first piece of this is to get our Vx and our VIY, or break it into components using our lesson 789 material. So step number 1, when I break this into components, I realize Vx is in the coast position, or the adjacent over hypotenuse. So when I do this, I'm going to go Vx is equal to, and now I'm going to put in that this is 180 meters per second, bracket, cos of 36 degrees. Okay, therefore Vx is equal to the magnitude. I'm going to try and hold on to as many decimals as I can. It's 145.62 meters per second. All right, now I'm going to do my VIY. My VIY is equal to, now instead of writing 180 meters per second times cos, because we used cos originally, now it's going to be sine 36 because it's the opposite over the hypotenuse. So therefore, VIY is equal to, the magnitude is going to be positive 105.80 meters per second. Excellent. There we go. Now, where we go from here is the following. we realize that we have our components now. So once we have our components, we want to see if we can figure out something from the vertical direction that we can pass forward to our horizontal, because they say, where does it land below? Where does it land below is eventually saying that we want to solve for our dx. So I'm going to write dx is equal to question mark, or the distance in the x direction is the question mark. Okay, on the next page, we're going to carry this information forward so that we can solve this. And it's going to start with the acceleration component, or us dealing with the vertical direction first. So let's hope there's a piece of paper here, which there is. Fantastic. I'm going to go step number 2, once we've broken that into components, is to say we have some sort of displacement in the y. We have a VFY, and I'm going to put VIY just because I like doing VIY first. VIY, VFY. We have acceleration, change in time. And change in time is always that question mark we want. The acceleration is in free fall, so it's negative 9.81 meters per second squared. VF, originally, I'm going to say that this might not have any bearing, so I'm going to put a line through it indicating that, maybe it won't matter, but maybe it will. And then I'm going to say this is equal to, for the VIY, our component for this was positive 105.80 meters per second. And lastly, the displacement in the vertical direction was that negative 125, negative because it falls down the cliff. Now, based on this criteria and these variables, what I would be tempted to do is do the following. I'd be like, oh, okay, I could put this into displacement y is equal to VI y multiplied by the time plus 1/2 AT squared. But if you remember anything about what we did in class here, you realize that we actually fell into a bit of a trap with this equation. And I don't want to fall into that again. And I don't want to leave us where we're having to do quadratic formula, because quadratic formula is not a prerequisite for this course. So if you want to use this formula and then use quadratic formula to solve this, you know what, be my guest. I think you can do very well with that. And it is another mathematical approach that is approved technically by the course and the course standards. But what I'm going to do is, because I see this t and this t squared, instead of using quadratic formula, which is a 20-1 skill, for now, what I'm going to do is just say, hey, let's not use this equation. This is a bad equation for us. What I instead want to do is solve for my VFY. Once I have my VFY, I can then use a different equation to figure out time. So here's what we can use. VFY squared is equal to VIY squared plus 2 times the acceleration times the displacement of y. So I'm going to put this as dy. Okay. Now, what we need to realize is that the reason this doesn't have vector symbols is because when I square root it, like I'm going to do in just a second here, I square root both sides. A square root always leaves me with a logical decision, and I'm going to write it maybe on the top of the page. If I square root, I can make this either positive or negative. And because this end value is heading in the downwards direction and it's right before it hits the ground, let's make that VFY a negative value. So what I'm going to do is, you could even put that above and be like, highlight the yellow, or highlight the negative, I should say, to indicate that this answer should be negative. When I do this, I'm going to get VFY is equal to the square root of, and we're going to put in all the values we have here. Starting off with the first one, it was positive 105.80 meters per second squared, plus 2 times the negative acceleration, negative 9.81 meters per second squared, multiplied by the displacement, which was negative 125. And I apologize for putting it in the second row. This is all being multiplied, so I'll even put a dot there just to show that that's multiplied. This is going to give me a VFY of, again, we want to put a negative here because this is talking about right before it hits the ground. And then what I need to now put is the magnitude. When I square root this, I get 116.82 meters per second. Excellent. Okay, now that we have our VFY, what I can do is, because it's going down, it's negative 116.82. This should make sense because it's been accelerated as it's headed down the cliff. I'm now going to say, okay, for step number 3, if I've found this VFY, let's use it to figure out what the time is from here. So now I have a VFY equal to negative 116.82 meters per second. And if this is my criteria from the previous part, now with the new filled in VFY, I'm going to use this criteria to use the basic acceleration equation to figure out time. So step number 3, I'm going to say acceleration is equal to VFY minus VIY, making sure to have the vector symbols on this one, divided by the change in time. Now, change in time and the acceleration are going to swap because I know from my math skills, if I multiply up the change in time, I'll eventually have to divide by the acceleration, and so they'll just end up swapping places. This is going to give me change in time is equal to VFY minus VIY, like so, divided by the acceleration. All right, now I'm going to plug in magnitudes here. For this answer, we have a VFY of negative 116.82 meters per second squared, or not meters per second squared, but just meters per second, minus the positive 105 meters per second that it started at. And this was 105.80, I believe, meters per second, divided by the acceleration, which is always our negative 9.81 meters per second squared, because that's our acceleration. Now, again, will the acceleration always be negative 9.81? No, not always, but the reason it is in this problem is because when we see that an object is close to the surface of Earth, we're just always going to assume it has this 9.81 that we've historically used in the past grades, like Science 10, for example. And then as we go into the later units, who knows, maybe as we get further away from the surface of Earth, this acceleration changes. But for now, let's hold it consistent. Therefore, here's what we're going to get. Our change in time is equal to, and this is going to be equal to 22.69. And I'm just going to hold on to a couple decimal places because we're not done our solution yet, so this will be totally fine. As long as we have 2 or 3 decimals, that's perfect. And ideally, if your calculator can store the value, I think for some of you, you may even get something like 22.693. Hold on to as many of these decimal places as you can. That's my biggest recommendation. And again, why do I highlight time? Not that it's the final answer, but we just got to make sure that we're holding on to these values that we're going to transfer between the two parts of this equation. And more importantly, between the vertical components and the horizontal components. Because no matter if I travel horizontally or vertically in this problem, it covers the same amount of time. Okay, now we go to our uniform motion equation. Vx is equal to dx is equal to, and change in time is equal to. The dx is what we're looking for. The vx, just to make sure I have this specific value, was 145.62 meters per second. The displacement in the x, or the distance in the x, my apologies, is unknown. And then the time is 22.69 seconds. Now, putting this together to get dx, here's what we're going to get, where vx is originally equal to dx over t, which is the first equation on the formula sheet. I'm going to multiply both sides by t, like so, and then this is going to give me where dx is equal to vx multiplied by t. Putting the values in, I'm going to get my vx was the 145.62 meters per second, multiplied by the time, which was 22.69 seconds, and then this is going to give us a dx value of, therefore, dx is equal to, and to 3 significant digits, I'm going to write out the calculated value first, which is 3,300 meters. But to 3 significant digits, we got to be very careful with this and say, therefore, dx is equal to, according to scientific notation, 3.30 times 10 to the power of 3. And this would give us to the power of 3 meters. There we go. And so when they say how far or what is the range of this thing, it is 3,300 meters. And the fact that it spent 22 seconds in the air is a reflection on the idea that we shot it vertically into the air at some degree. And so if it's not being shot horizontally, it's being shot at this really, really fast rate. Like we're talking in the hundreds of meters per second. If it's being shot that quickly and vertically, it's going to spend not only a lot of time in the air, which 22.69 seconds is a lot of time in the air, but it's also going to travel a very far distance in terms of the dx, especially with an angle of 36, because that's not like it's like 90 degrees, for example, straight up and down. It's something that is kind of between 90 degrees and 0 degrees, and roughly it's almost in the middle of that. So it will travel a decent amount in the x direction or decent amount in the horizontal direction. All right, that does it for all our examples. I highly, highly encourage you to get a ton of practice around these things. Projectile motion is not an easy concept, and when you get the idea that you're passing information backwards and forwards, namely the time between uniform motion and accelerated motion, and vice versa, accelerated motion to uniform motion, when you get that idea that you're passing that time back and forwards, it will make a lot of sense to you and you're going to start to piece this together very quickly. But I do recommend do all the practice problems in this section so that you really emphasize that you understand this stuff, and you, just like I said in the last lesson, work towards that idea that you're mastering the content and not just being comfortable in this kind of concept of passing information backwards and forwards and blending all the concepts that we've talked about through lessons 1 to 9 to this point. All right, good luck with your practice.